Next speaker is Julian Wykowski from the University of Cambridge, who will speak about profinite rigidity, Noetherian domains, and solvable groups.
Thank you very much. I'm very happy to be here at the workshop on discrete and profinite groups. I'm speaking today about a topic which is central to the connection between discrete and profinite groups, which is profinite rigidity, absolute profinite rigidity. So let me start right away by fixing some terminology. So a finitely generated residually finite group so I'm going to abbreviate this just as all got it this morning, is profinitely rigid in the absolute sense. Is the only type of profinite rigidity I will be speaking about today. If for any other finitely generated residually finite group delta, an isomorphism of profinite completions implies that there has been an isomorphism of discrete groups to begin with. And this first part is, of course, equivalent to the property that the sets of finite quotients of gamma and delta are equal. And the question is then, which groups are profinitely rigid? And this question is now more than half a century old. It started with Grothendieck, who was studying étale fundamental groups that, given a complex variety, the étale fundamental group recovers the usual the profinite completion of the usual topological fundamental group. And group theorists were studying decision problems, and so this question naturally arose: to what extent can you determine an infinite discrete group in its finite quotients? And the first results appeared around 1970. So there was a theorem first of Pickle in 1970, who proved that finitely generated nilpotent groups are almost profinitely rigid, which means that for any such group gamma, you have at most finitely many other groups which have the same profinite completion as gamma. But in fact, from his proof, you can deduce that for certain finitely generated nilpotent groups, they are actually profinitely rigid on the nose. So this is certainly true for abelian groups. That's an easy proof, but later papers appeared where people were distilling this proof and actually proving absolute profinite rigidity on the nose for certain classes of nilpotent groups. And then 10 years later, Pickle, Grunewald, Pickle, and Segal extended this result to finitely generated polycyclic groups, virtually polycyclic groups. Okay, so these were the first results around that time. But in the same decade, Baumslag, he produced the first interesting example of failure of profinite rigidity. That was in '74. And this is a very, very famous example where he showed that you can take the cyclic group of order 25 and you can take the extension by the infinite cyclic group, which acts as multiplication by 6, and that's going to have the same profinite completion as the same group, except where Z acts as multiplication by 11. But these groups are not discretely isomorphic, and that's a virtually cyclic group, so as nice as it gets. And in the same year, Pickle, who was a student of Baumslag, he proved that there exist finitely presented, in fact, meta-abelian groups. So this means solvable of derived length 2 with infinite profinite genera. So for each of these groups, there exist infinitely many pairwise non-isomorphic groups delta, which have the same profinite completion as one of these groups gamma. And so that kind of killed the question at the time, because the class of meta-abelian groups is really the next most natural extension that you could look at after nilpotent or polycyclic groups. And if there we already have kind of maximal failure of profinite rigidity, then in what classes could you possibly have profinite rigidity? One such class was asked by Remezlenikov. This was mentioned yesterday by Andrei. This is now an infamous question. So he asked this question for free groups, but he also asked, and this is less known, so our free groups. So he also asked in the same question whether free solvable groups are profinitely rigid. So by the free K solvable group, I mean the maximal solvable quotient of a finitely generated free group, which is solvable of derived length at most K. And this question has been open ever since, and the first part is has attained fame. The second part is, in fact, what I want to speak about today. So after,
was it
yes,
even for free pavilion or?
yes. So so this was the question of Remezlenikov, and then since the 70s, for the next 4 decades, there were actually no new positive results of absolute profinite rigidity. There was a lot of interest in profinite rigidity. We had relative results, we had counterexamples, a lot of counterexamples, some some counterexamples that are among my favorites are certainly the original question of Grothendieck got disproven. That's a bit of a stronger question that asks about the profinite rigidity of a specific map. That was disproven by Platonov and Pavgen for finitely generated groups, and then by Bryson and Grunewald for finitely presented groups in 2003. And also a very nice result was proven in 2017 by Nikolov and Segal. They proved that there exist solvable groups of derived length 4 which have uncountable profinite genera. So there are uncountably many pairwise non-isomorphic groups with the same profinite completion, and they're all solvable of derived length 4. And then in 2018, there was a breakthrough in 2018. There was a team, Brightson, McReynolds, and Spittler and Reed. They proved, they constructed the first example of absolute profinite rigidity for groups that are full-sized. So groups that contain a free subgroup. These were given in this instance by certain arithmetic Kleinian groups. And then there were a few results in a similar vein by the same authors and by some other authors as well. And then in 2024, there were 2 new results about profinite rigidity. So one of them was that affine Coxeter groups were profinitely rigid. This was proven by 2 independent teams. Olga spoke about it earlier today, mentioned it earlier today. And the second result I would like to write down, this appeared on the archive in November of last year. It was proven by a person called Blachar, and he proved that Lamplighter groups of the following form, so Lamplighter groups with exponent, with base of prime exponent, these are profinitely rigid in the absolute sense. And why am I mentioning this last result? I'm mentioning this last result because the proof of this result was very much along the lines of this paper of Pickle from '74. These two papers are very similar in that instead of considering the finite quotients of the group itself, which in general, because the category of groups is can be very untamed, very wild, is a hard thing to do. Instead, these authors passed to a certain module that arises as a representation of that group and considered the finite quotients of that module. And these are simpler to study because in algebraic categories and in categories of modules over group rings, you have much more structure in general than in the category of groups. And so what Pickle did is he used this to produce isomorphic non-isomorphic modules which have isomorphic profinite completions. And what Blatchard did is he showed that for a very specific ring in this case, which is a well-behaved ring, it's a principal ideal domain, you know actually enough things about modules, about the structure of modules over that ring to prove that this group is profinitely rigid in the absolute sense. And when I saw that paper, it made me think whether perhaps there can be an approach to profinite rigidity that is more streamlined, that starts with a general category of modules over a commutative ring, and then erects a theory of profinite rigidity in that algebraic category, which could give you more applications, more groups at the same time. So the idea would be kind of to go away from proving a specific group or a small class of groups at one time, but instead consider first this algebraic question, and if you manage to answer the algebraic question for a nice class of rings, for instance, then you could attack much larger classes of groups at the same time. The dream being, perhaps, you could attack something like all metabelian groups, or one day even all solvable groups or of higher derived length, and categorize which groups there are profinitely rigid. And so I started researching such a theory, and for a certain class of rings, I did that in my previous project. These are the class of Noetherian domains. This is what I'm speaking about today. And but really, the assumption of Noetherian domains makes my life easier. But really, I don't believe that any of the steps in any of the proofs is really extremely essential to there being Noetherian domains. I think this is the first step in a more general idea where we could consider larger classes of rings and larger classes of groups in general. And so as an application of this theory, I was able to prove profinite rigidity for two classes of groups that I find of significance already now. So I will mention this now. So this is theorem A. So the following groups . So the first class of groups is the class that we had a question about, free metabelian groups. So these are the maximal metabelian quotients of the free group. On n generators, or equivalently, this is the quotient of the free group on n generators by the derived subgroup of the derived subgroup. And the second class is solvable Baumslag solitary groups. So the Baumslag solitary groups are indexed by two integers, and if one of those integers is 1, then the group is solvable, and the other one can be any integer here. And and this can be any natural number. And so the first part of this theorem contrasts with this theorem of Pickle, who proved that in general this doesn't have to be true for metabelian groups. And it also answers the solvable side of Hermes-Lennikov's question for k equals 2. K equals 1 is, of course, a trivial case, but k equals 2 is sort of the first non-trivial case. And I believe that number 2 is the first known example of a non-abelian one-relator group to be known to be profinitely rigid in the absolute sense. So let me say a few quick words about the sketch of this proof, and then I'll get into details. So the idea is in each of these cases is that if you have a group which contains an abelian, let me do this a bit more on this side of the board. Actually, so if you have a group gamma which contains an abelian normal subgroup M, and this subgroup is distinguished in a certain sense, by which I mean that it satisfies some kind of law that is detectable in the finite quotients. And let's also assume that the quotient by that normal subgroup is very nice from a profinite perspective. So in fact, for the purpose of this talk, let us assume that this is distinguished, and let us assume that this is already known to be profinitely rigid. Okay, and you have this short exact sequence. And then, of course, this will induce the same short exact sequence on profinite completions, except we have to take closure here instead of completion for this subgroup. And then suppose that there exists an isomorphism of this profinite group onto the profinite completion of any other group delta, then by this condition of M being distinguished in the sense that we want, so examples for this could be, it could be, for instance, the commutator subgroup, or it could be the maximal nilpotent subgroup, the fitting subgroup. So the commutator subgroup is something that we will be using in this proof, but the fitting subgroup, this is something that very much appears in these ideas of Grunewald, Pickle, and Segal. They were really working with these fitting subgroups. And then you know that your delta also has to have a subgroup that has this distinguished significance. And you can likewise complete this part of the picture in such a way that this isomorphism restricts to an isomorphism here from M, from the closure of M onto the closure of M. And now the point is that in general, even though it is abelian, this M and N, they will not be finitely generated abelian. So they will be, so there's no sensible theory of profinite rigidity for non-finitely generated groups. And so what we want to do is we want to work with a bit more information. We want to work with the fact that these are not just the completions of these infinitely generated abelian groups. We want to work with the fact that they actually they are the closures within this completion of the ambient group. And the way that we can express this algebraically is that there is a structure of M as a ring, as a module over the group ring of this quotient group, where the quotient group acts as conjugation within gamma and likewise for N within delta. Okay? And this is, let me call this group lambda. And now if you want to prove that gamma is actually isomorphic to lambda, then you need to solve two issues. First of all, you need to develop a sensible idea of whether M, yes. you need to develop a sensible idea of whether M is profinitely rigid as a module over this algebra, because this is exactly what encodes the fact that it comes from conjugation within this ambient supergroup. So is M profinitely rigid as a lambda module? And the second part is much more subtle, but in fact it is much more important, which is that this map F over here, this is an isomorphism of abelian profinite groups, but it's not in general an isomorphism of modules. Why? Because over here, on this y factor, gamma, this isomorphism of profinite groups induces an automorphism of this profinite completion of y. And so instead of being an isomorphism of profinite modules, what this F is it's like a twisted isomorphism of modules. Meaning that if you multiply an element by an element of the ring, then that's the same thing as first twisting the element of the ring and then multiplying the image of your isomorphism. And this is exactly what happens in these examples of bounds like here. So in these examples, the module we can define to be this finite module. So of course it's profinitely rigid, it's a finite module. But in fact what happens is that when you draw this diagram, you obtain an automorphism of the p-adic integer, of the profinite integers, which is congruent to 2 mod 5. And that's fine because the profinite integers have generators that are congruent to 2 mod 5, but the regular integers, of course, do not have such a generator. So that's how you get an automorphism there, which doesn't arise as an automorphism of the discrete groups, and that's how you can get these kind of counterexamples. So this subtlety is very key to the proof, and what we will want to do is we will want to untwist this. So we will want to, from this isomorphism, produce an actual isomorphism of modules. Now this first part is along this... Yes?
How do you have an automorphism of y rather than y?
No, I meant of y hat. Yeah, so alpha is an automorphism of y hat.
Right. But your modules are only over lambda, not over its completion.
Right, but then, okay, so I'll get to this a bit later, but in this case, it turns out that if you take the closure of the subgroup and you consider the module structure of that is given by conjugacy within this profinite group, this is the same thing as considering the completion, the profinite completion of the module as a module over the group algebra of y. So then you obtain a structure of the completed group algebra on M hat, and this is now the completion.
But your untwisting is really going to be defined on. Where's your untwisting going to be defined? Where's that alpha?
This alpha is in here. This is all profinite. So this is entirely the profinite world. Okay. Yeah. So precisely the point. If you had a discrete alpha, then you would be done. You wouldn't have to do this. Okay. And so this first step is really along the line of the philosophy that I'm trying to sell here, is that you can do this sort of systematically for this whole class of modules over a ring. But the second part, unfortunately, in my current idea of things, I have to do it by hand for each of the 2 classes of groups. So that's something that I haven't managed to bridge yet into the sort of systematic idea. But nonetheless, both the proofs, which I hope I will be able to get today, both of these proofs are, the untwisting part is really a common iteration among a theme there. So also there I have a belief that this is sort of a shadow of a bigger thing that's going on there, that ultimately it might be within reach. Soon we could generalize this to something like a broader class of metabelian groups, or maybe even all metabelian groups. Okay, so I will now start the second part of my talk, which is about Noetherian domains. But in the meanwhile, I want to ask if people have more questions.
One question.
Yeah.
So in the two examples you gave, that particular sequence is split. How important is this in these two?
Yeah. So in the two examples I gave, this short exact sequence is split.
No, actually, in the Bamsar side only.
It is. But so in the Bamsar case, this is not the derived subgroup. I'll get to this later, but it's the kernel to the maximal torsion-free abelian quotient. And so that is also split in both cases. If it's not split, then technically you have to do a little bit more work, but you can do it because essentially abelian groups are good. So, or if you assume that Y is in general a good group, then you can work around it being split. But this is not necessary.
But not in general. If it's an abelian bifinite, there are abelian bifinite with an isomorphic lattices in this sense, but they are not profinite rigid.
Yes, precisely because of the failure of this second one.
But there are examples in which
Yes. Yeah, I'm just saying what happens there is not whether it's split or not. This part is not what fails.
There are examples in which the split extension is fine, but then there is a non-split extension with the same modular structure which is not profinite rigid.
And Y is abelian in those cases or not?
Y is not abelian. It's
Okay.
abelian by gamma is abelian bifinite, Y is finite, but it's not abelian.
Okay, yeah, I was talking about the case where Y is abelian. Yeah.
Why did you want to restrict yourself in Baum-Solvable group only to solvable cases?
I think the other cases, so the only other residually finite Baum-Solvable groups are BS n and plus minus 1 n. And I think those are going to be substantially harder. I don't see why. So these are no longer.
Baum-Solvable group, those which are residually finite, I understand they pretty well understood, I think.
I mean, they're not solvable, so these methods.
Yeah, they are not solvable, but I mean, since you did already solvable.
Okay, maybe in the future. Anyway, this talk is about solvable groups.
And I have a question. If
Yeah.
you have torsion abelian by abelian,
Yeah.
do you expect rigidity or
If I have torsion abelian,
by abelian?
I mean, in general, no, like this example of Bamsak. Or do you mean if you put torsion here?
Torsion, but it's
You
not
mean if it-
torsion abelian, is it torsion
You mean
abelian?
if you
Extension
flip it around, or?
I mean, subgroup is torsion.
Yes, so
And
this,
the torsion, also this example Bamsak already.
yeah.
What about Z?
What about Z reset? Working on it. Any other questions? Okay, good. So let lambda be a finitely generated commutative domain, and so in particular it will be Noetherian because of the Hilbert basis theorem. And let M and N be finitely generated lambda modules. Okay, so here's a few observations that are not hard to see. So first of all, exactly like in the category of groups, so let me define. So we're going to consider the profinite completion of our modules, but this is of course in the category of lambda modules. So that means we're taking the inverse limit of quotients of our module by finite index submodules. Okay, and then the question becomes, you know, when are these modules profinitely rigid? So when does it hold that an isomorphism of profinite completions implies an isomorphism of modules? And so a few easy observations to begin with. First of all, an isomorphism of profinite completions for finitely generated modules is equivalent to the statement that the sets of finite quotients are the same. It's exactly the same proof as in the category of groups. And likewise, if we know that the profinite completions are isomorphic, and we know that one of the modules surjects onto the other, then we also know that the modules themselves are isomorphic. And third, this is different from the category of groups. Every finitely generated module is residually finite. So we don't have to, we can drop residual finite from all our statements here. This is, I believe, a result of Reeves, but it's not hard to see either. And then two things that are a bit less immediate, but I hope you'll also believe me when you see them. So first of all, if you take a maximal ideal I in your ring lambda, then an isomorphism of profinite completions of M and N implies that if I take my module M and I localize it at that ideal, and I take the completion of that, that is the same thing as taking the completion of this tensor product. And that in turn, you can prove is isomorphic to the completion of M completed tensor product over the profinite completion of lambda with the I-adic completion of lambda. So this is the completion of lambda by the filtration given by all powers of I, which is an exhaustive filtration in the case of a domain, of a Noetherian domain by a closed theorem. And this isomorphism here is not immediate. You need to, because in general, completed tensor products do not arise as are not. In general, you will not have such an isomorphism of tensor products, but in this case, because things end up being local, I hope you will believe me. It's not hard to prove that this isomorphism holds as well. And then, of course, once you have this and you know that the profinite completions of M and N are isomorphic, then you get an isomorphism here on this factor, and this part is independent of M and N. So then you find that this is also isomorphic to the profinite completion of the localization of N at the same ideal. And in a similar vein, if you make the same assumptions, then the number of generators of the localized modules will be the same. This is essentially Nakayama's lemma. Okay? So here's are a couple of observations you can write down with just a tiny bit of algebra, but something that we can now prove using only these ingredients. Yes?
So, as I understand, this completed tensor product, you can also put a normal tensor product, no, in this case, because you have finite less product. Finally presenting more.
I mean, in the case where lambda is, yeah, I suppose. Yeah, the point is you, in general, for tensor products, you do not have this isomorphism there, even if you put the normal one. But yeah, but in this case you do. And something that we can prove now is that being projective of rank n is a profinite invariant of lambda modules. Why is this true? Because being projective is equivalent to every localization at each maximal ideal being free of rank n. And so if you have a module and you know it's projective of rank n, every localization is free of rank n at every maximal ideal. So you know by this part that the same is true for any other module n that has the same profinite completion. And you know by this part that any other module n which has the same profinite completion, its localizations will then be profinitely isomorphic to the free module over this local ring of rank n. But then you also know that their number of generators are going to be the same. And if one of the discrete modules is actually the free module, then you're going to, of course, have a surjection of that localized module onto the other localized module. And then you can use number 2, where you know that you have a surjection and you know you have an isomorphism of profinite completions to find that you actually have an isomorphism of the discrete localized modules. Now you know that your other module n is also locally free of rank n, or equivalently projective of rank n. Okay? And so this is one proposition, but an immediate corollary is that if your ring lambda, something that I like to call homologically taut, which essentially means that every projective module is free, then free lambda modules are profinitely rigid. Because then you only have one isomorphism class of each projective module of rank n, which is the free module. And this might seem like a very restrictive condition, but in fact, we have an isomorphism, we have a theorem of Quillen and Suslin that has been very celebrated. I believe Quillen received the Fields Medal partially for this theorem. That the free algebra on n generators, the free commutative algebra on n generators, is homologically taut. Okay, and from the proof of Suslin, you can deduce that the same thing is true if you allow also the inversion of every one of these generators. So then you get the group ring of Zn, and this is what we will be using in this theorem. Okay? And then another 2 results that won't be necessary for this application, but you're able to prove using this theory is, first of all, that if you have a ring which is a Dedekind domain, so now we're not assuming that it's homologically taut, but we are assuming that torsion-free and being projective is the same thing. So for Noetherian domains, this characterizes Dedekind domains. Then over this ring, there exists a structure theory which is very similar to the structure theorem of modules over a PID, except there exists some ambiguity regarding the projective modules. And that ambiguity is captured by something called the Picard group, or the ideal class group of your ring lambda. And so then what you can prove using that structure theorem is that the profinite genus of every module embeds into that Picard group. Okay, and so in particular, if you have something like the ring of integers in a number field, then that is a Dedekind domain, and its Picard group is finite. So then you know that all finitely generated modules are almost profinitely rigid. And this, for instance, gives you an immediate proof that solvable free manifold groups are almost profinitely rigid, which is known also because they're virtually polycyclic from this theorem of Grunewald, Pickle, and Segal, but this proof is somewhat faster. And in particular, if lambda is a PID, then it's a Dedekind domain with trivial Picard group. So then every finitely generated lambda module is profinitely rigid. And this then gives you also the proof of Blatchar about these groups, because here you can work with the group ring of Z with coefficients in Fp, and that's a PID. Okay, so that finishes the second part of my talk. I will now get into details about this proof over here. I'm a bit tight on time, so I will not ask for questions this time, but please ask them after the talk. Okay, so suppose you have a group gamma, which is one of these groups, and we're going to do exactly this whole game here. We're going to assume that this is either equal to or virtually equal to the abelianization of to the commutator subgroup of gamma, and so this is going to be either the maximal abelian quotient or the maximal torsion-free abelian quotient, and we're going to have that lambda is equal to the lambda is going to be equal to the I'm going to leave y here, but it's going to be equal to the group ring of the abelianization or the maximal torsion-free abelian quotient. And so how can we untwist so the first part of this whole strategy, the question of profinite rigidity for M, this is going to be solved using this theory I just presented. But how can we deal with the second part? So how can we untwist, if we have such a twisted isomorphism, how can we untwist that? So yeah, just as the question we had earlier, this holds for all lambda now in lambda hat and for all m in the profinite completion of M as a module, which turns out to be the same thing as the module structure on the closure of M as an abelian subgroup obtained by conjugacy within the profinite supergroup. Okay, and so what happens now? So in the case where M is a free module, untwisting is not hard, because if M is a free module, then you can simply do something like this, where you have an isomorphism. M hat is isomorphic to this module, and then you compose that with this twist, which is an isomorphism of rings to the nth power, and that is an isomorphism of rings, which gives you this weird map on the modules. It's not an isomorphism of modules, but you compose this with this twisted isomorphism of modules, and the composition suddenly becomes, you see how it untwists itself, suddenly becomes a bona fide isomorphism of profinite modules. So that's easy, but unfortunately neither of these cases the module is free. One would think for free metabelian groups it would be free, but it's not. It's only free in the case n equals 2. So what is true in both of these cases is that M is free over the ring obtained by quotienting lambda by the annihilator of n. Okay? And so what we want to do in that case is we want to take our isomorphism and we want to descend it over to an isomorphism of the quotient here, and we're gonna, and this is gonna give us an isomorphism which takes us to the quotient of lambda hat by the annihilator of the profinite completion of M. This is given by the twisted relation. But the issue is that in general for modules, it is not clear how the annihilator of the profinite completion behaves with respect of the annihilator of the discrete module. So you would want to have something that looks like this, where you take the annihilator of the discrete module, you take its closure within this profinite ring, and you have an equality. But whether or not that holds in general is actually turns out quite hard. And actually, I can show that for quite a lot of modules, it's equivalent to this notion of ideal closure, integral closure of ideals in quasi-local rings, which is actually an active area of research in commutative algebra and algebraic geometry. But it's possible in the present situations. So in the present situations, we will know what M is, and so it will be possible for us, it will be quite easy to show this. For instance, for any cyclic module, it's almost immediate that this holds. We will not know what N is, but we will know enough about N from its profinite completion being isomorphic to that of M to also be able to devise this equality. I don't want to get into these details because I'm hiding quite a lot of algebra here, but just believe me for now that in the modules that we have here, this is indeed true. Okay, and so let's dive into the proof in the last 13 minutes. So, as said for free meta-Abelian groups, the module unfortunately is not free, but there is an alternative module that is free, which we can work with. And so how does that work? So we are now assuming that gamma is free meta-Abelian. Of rank n. And we then have a short exact sequence that looks something like this, where the module is simply the commutator subgroup of gamma with canonical structure, and the quotient is the Abelianization, which in this case is isomorphic to Zn. And this module is not free, but what you can do is you can take this extension. This defines a class in the H2 group of this Abelianization with m gamma coefficients, and that is, we know via algebra, that is isomorphic to x1 over the ring lambda. So lambda is the group ring with z coefficients of the Abelianization. And we have an isomorphism here where we take the augmentation ideal here of the Abelianization, and here we take m gamma. And this isomorphism maps this extension to the following extension. So we have 1, so we have 0, this is now extension of modules, 0 to m gamma, to the module E gamma, which I define as the group ring of the Abelianization tensored over the group ring of the whole group with the augmentation ideal of the group. And this is going to map onto the augmentation ideal of the Abelianization. This extension is exactly equivalent to this extension by this isomorphism. And now there's a theorem of Groves and Miller from 86 that if gamma is meta-Abelian and the Abelianization of gamma is Zn, then E gamma is free over lambda if and only if gamma is free meta-Abelian. Okay, and so we know that this other module is free meta-Abelian, and so what we want to do is we want to work with E gamma instead, and we want to prove that E gamma hat is isomorphic to E delta hat. And the hard part is in here is showing that the completion of this, which is given by the completion of this tensor product, that the completion of this tensor product is in fact isomorphic to the completed tensor product of the completion on each side, so of the completed group algebra here. Completed tensor product with Z gamma hat. And what you need to do in proving this isomorphism is essentially you can consider this notion of goodness for modules over this ring, and you will find that this isomorphism follows from the goodness of the free abelian group. And so I'm going to call this E of gamma hat. And once you have this, then you can say, okay, well, now E gamma hat, that is isomorphic to this thing, and this has an isomorphism over the same thing with delta, because the abelianizations, of course, are isomorphic. And what we can do, we don't want just any isomorphism here, we want the isomorphism that is induced by this twist tensored with F, with the induced map on the augmentation ideal. And if you do that, then this twist is going to cancel itself out, and this is going to give you an actual isomorphism of profinite modules. So then this, by the same argument as there, is going to be E gamma hat, which is going to be this, or E delta hat. But now we know by Groves-Miller that this one is free, so we can use the corollary from our theory of Noetherian domains to deduce that it's profinitely rigid. So actually, so here we're of course using this Quillen-Suslin theorem because this is precisely this free commutative algebra. So actually these two modules are isomorphic, and then we use Groves-Miller again to find that delta must also be free Abelian. Okay? Okay, and for the Bamstek, so this was free Abelian, and now for the Bamstek-Solitaire case, it's a bit more involved. So let me just really sketch it. So assume that gamma is BS1n, so this has the structure of the ring of Laurent polynomials in one variable modulo the ideal generated by x minus n, semi-direct product z, where the generator of z, let's call it t, acts as x. And this was gonna be my module m that I'm working with. And now here we really need to play this whole game of annihilators that is over here. And essentially, because m is a cyclic module and n hat is isomorphic to m hat, using some tricks and a lot of Bourbakis for sure, you find that gamma, that delta, if you consider the module that arises in the same description of delta, then n is gonna have satisfy this relation of annihilators that we want to satisfy. And because we know that this twisted so we have this twisted isomorphism from m hat to n hat, we know that this other annihilator is equal to the same one for m, except passed through alpha. And that is going to be the closure of x minus n. And now we just basically play with ideals in lambda, because this is a linear principal ideal. It's locally prime. You can play with this iadic completions and find that the annihilator, the abstract annihilator of n, must also be locally prime. And in fact, it must be principal and linear as well. So what you get is that it is equal to ax minus b, some kind of linear polynomial, where a and b are two co-prime integers. Okay? And so now you can consider this ring chi n, which is lambda mod the annihilator of n, and you find essentially that your twisted isomorphism exactly in this way. You can untwist it. I'm not going to write out the details to get that chi n, the profinite completion of that ring, is isomorphic to the profinite completion of n, and then you use this theory with chi n instead of lambda, which in this case is actually a PID, so you can use either the full theory of, or this equivalent cysteine theorem, whichever you prefer, to get from this that chi n is actually equal isomorphic to n. And now one would think you're done, but you're not completely done, because you haven't proven that it's exactly what you want. You have proven that delta has this form. And surely then finding, so here z acts as x, and equivalently this is the same as acting as b divided by a. And surely one would think then it's not so hard to show that b divided by a has to be actually equal to n. But actually, if you consider the profinite completion of this, which is now the product of all p-adics that do not divide AB, semi-direct z hat, where z hat acts as this b divided by a, gamma has the same form, except instead of b divided by a, you have n. So you know that a prime number p divides AB if and only if it divides n. But can you conclude, using everything that we know, that is actually isomorphic to the Baumschlag-Salter group? Well, it turns out actually that this is equivalent to a question in number theory asked by Erdos in the 80s, and then resolved in 97 by Corrales and Schoof, two number theorists, which says that if you take two rational numbers and you have the property that the power of chi is congruent modulo to p to the power of mu for every power k and for almost all primes p, almost, so in this case all that do not divide AB, then actually chi and nu have to be equal or inverse to one another. And if you apply this to our theorem with b divided by a and n, then you find that b divided by n has to be equal to n plus minus 1, but of course b and a are coprime, so it follows that one of them is 1, the other one is n, and gamma is isomorphic to delta. Okay? And so I have 38 seconds. I wanted to write down two questions, but I'll just tell them verbally. So yeah, these groups, I have chosen them because I like them, because they appear in group theory in various places. But as said, I do have the dream that we are not too far away from actually attempting all meta-abelian groups, and perhaps one day we could even attempt higher derived length solvable groups. And if we were able to define a good theory of profinite rigidity for modules over the group rings of higher derived order free solvable groups, then that would almost immediately give us a solution to the solvable part of Remeslianikov's question. Thank you.
Any questions?
metabillion groups, because they're examples of metabillion groups of genus, right?
Yeah.
So what is your kind of? Do you have a conjectural expectation? What will be the description of the rigid metabillion groups?
No, I don't have a conjecture. I don't know that much about the general structure of metabillion groups, but what I think is that actually from these methods, we're not far from, if you attack one or two more groups, you're not going to be that far from understanding maybe at least when is it profinitely rigid, when is the genus infinite, and when it's finite. Maybe you're going to be able to decide that. So of course, there's going to be examples of all of those, but you're going to get some kind of argument that can phrase this equivalently in terms of some algebraic condition. But I don't have any conjecture.
I have two questions. One, I try to formulate better something I tried already to ask. If you have p torsion abelian group by abelian, for many questions about metabillion groups, this class is easier than torsion-free groups. Here, do you expect rigidity, or maybe can prove something? Like p torsion abelian by abelian.
So do you mean that the p torsion
subgroup is a p torsion abelian, and
Yeah.
the quotient is abelian?
Yeah, here I would, so of course I haven't verified it, but here I would be willing to conjecture that these should all be rigid, essentially, because then you are in this case, and then instead of working with z coefficients, you can work with fp coefficients, and then it's a PID.
Yes, so in all these questions, you have modules of a group or polynomials or Laurent polynomials over a field rather than over Z,
Yeah.
which is easier.
Yeah,
right?
yeah.
Yes,
Yeah, so there's still this matter of twisting things. So, okay, so in this first case, then you will automatically get profinite rigidity by my result about PIDs. But there is still this matter of twisting, right? So this is, for instance, this bounce-like examples are exactly counterexamples. So,
but the bounce-like result, your torsion is not prime, right?
I mean, it's a prime power. You meant actually just
Actually
prime.
P torsion.
Yeah.
Can you maybe prove if it's really P, not a prime power, P torsion by
That you can always untwist it. That's a good question.
Maybe the easiest case you mentioned free metabillion. If instead free metabillion you take free p metabillion, that is, you take a free metabillion group and you quotient the commutator by power of p equal to 1.
Right.
I don't know if you.
Yeah, that's a good question. I seem to recall somewhere in my memory that there were examples like that of bounce-like, where instead you took 11 instead of 25.
So there are non-rigid examples with torsion which is just 11.
Yeah, if you put 11 instead of 25 there and some other numbers for the action, then I think these examples also exist.
I think 11 is minimal number.
Maybe. I mean, you need a prime, you need it not to be 2 or 3 or 5, I guess.
My second question, you mentioned that split or split is not so important. Can you have a general phenomenon like this if you have some extension, or you have some abelian group, so extension by some abelian group, by some other abelian group, which is maybe not split. If you, this is your group G, if you consider the group G2, which is extensions of exactly the same groups with the same group actions but split, is it true that if the split case is rigid, then the non-split is rigid as well, or you have less general statement?
That's a very good question. So yeah, I mean this. I don't know on the top of my head if this is true or not, but I think essentially you can phrase these questions in some equivalent way in terms of the goodness of H2, or yeah, just comparing the finite and the discrete and profinite cohomology. And so I think there must be ways to answer that question, but I don't know it off the top of my head. Yeah.
So concerning finding the dividing line, you were saying so something like you have the module, you pass to the endomorphism ring, so knowing if every locality is free, is the same thing as being profinite rigid. Would this be a satisfactory answer if I were able to show this?
Sorry, can you repeat? I don't think.
So you have your lambda.
Okay.
Gamma. So when we reduce the problem, going through the endomorphism ring, if all the locally free, which means projective of rank 1, are free, this is the same thing as the module being profinite rigid that you started with your
Sure.
end. Would this satisfy you as an answer?
I mean, as an answer to...
you were saying you want to decide when they are profinite rigid, when the genus is free. So this would be an exact algebraic characterization of when it's profinite rigid. This is the best I can do.
Right, okay, but this is a characterization in terms of a homological algebra, right? What I meant is more like an algorithm.
This is what you do for the genus problem in number theory, and I can do it with many many rings. I ask because I'm doing this, so if you would be interested.
Of course, it's nice. I think, I mean, probably the other direction is not so hard to do this. Ultimately, I mean, what I meant by decidable is something that you plug in your group and you can tell whether that's the case. And to test if something is projective or not, it's not, it's probably also not so easy algorithm.
Okay, so let's thank Julian.